our understanding and made this session truly meaningful, sir. We are grateful for your time and effort, for your dedicated to be with us, for sharing your knowledge. Once again, I'm thanking you, sir,
Yeah,
for
thank you, Dr.
providing
Vinod.
this
So once
opportunity.
again, I thank all the participants for listening to my lecture. You're most welcome to write email to me for any queries.
Sure, sir.
Okay, thank you once again to all the participants. And I request Dr. Vinod, you can share my, I will send this PDF file of my presentation. You can send it to all the participants actually.
Sure, sir.
Okay, thank you. Hope I can sign off.
Thank
Once
you, sir.
again, thanks to all the participants. Thank you so much.
Sure, sir. Sure, sir. Thank you, sir. So it's time to start our second session. So it's my due. No, sir. Shreyans, sir.
Yeah,
Hello.
good evening, all of you.
Hi, sir. So sorry, sir. Sorry for the delay. So it gives me a pleasure to introduce our next team, esteemed speaker, Shreyas Khot, sir. A seasoned professional with 13 years of rich experience in the field of new product development, defense and aerospace product development, material characterization, quality materials, and additive manufacturing. Mr. Khot is highly skilled in areas such as metal additive manufacturing, reserve engineering, IP management, and design for additive manufacturing, laser physics, machine building, and machine business development. His manufactured experience has made a significant contribution to India's to achieve manufacturing ecosystem. He has spent nearly 12 years at Bharat Forge Research Development, serving in a various strategic role where he was deploying now in a cutting-edge R&D activities. For the last 3 years, he has been associated with AMACE Solutions Bangalore. We are pleased when he played a key role in developing India's first metal 3D printing machines, a remarkable achievement in the country's manufacturing innovation landscape. Mr. Ketan holds Masters from M.Tech in material manufacturing and modeling science from prestigious institution, Indian Institute of Technology, Bombay. We are honored to have with you, Esther. We are we are looking forward to gain valuable insight forms in vast experience in additive manufacturing and product innovation. We are welcoming you, sir, for this session.
Thank you, Professor, for the nice introduction. Am I audible, all of you?
Sir, you are audible, sir.
Okay. So, shall we start the presentation?
Sure, sir.
Okay. My screen is visible.
Yes, sir, it's visible, sir.
Okay. Shall I go for full screen or it is okay for this particular screen?
Sir, you go with the full screen, sir.
Okay. 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 Then. So, okay. So, we will start with this particular additive manufacturing, and then this will be the my brief overview of the presentation flow. Initially, I will go with the global overview and present state in India. What is the key government initiatives? And then we will follow with the current status in India. What is the current status? In the then it will be followed by additive manufacturing process flow. And then what are the key challenges we are facing, industry is facing for this particular additive manufacturing, and then it will be followed by the some research developments. So I will present the latest case studies, including all this particular, starting from the aerospace, space, automobile, dye and mold, jewelry, medical, all the case studies, and then a few slides for this AMACE offering. What AMACE is offering for this particular industry, additive manufacturing industry. So I'll be the crisp presentations. I have particularly put only 30 slides only to give more time for this particular interactions. What are the your question and answers are there. So going forward, this will be the slides. This is our group introductions. You can see this particular, we are from the ACE Macromatic Group company, where we have started with 1973, which started with the micromatic grinding. And slowly we have moved with the Pragati Automation, Tool Turret, etc. This is our flagship company, ST Designer, where we are making the turning solutions. And then this is the AMS, another group company, where we are making the HMC and VMC machines. In 2018, we started with the AMACE solution dedicatedly for this particularly making 3D printing machines. Apart from this, we have some IoT and Industry 4.0 IT company, laser cutting machines, and then some special purpose machines. So this is a glimpse of the S Micromatic Group company. We are present in this more than 4 decades. And then 2018, we started with AMACE. The two flagship companies, ACE Manufacturing System and ACE Designer came, and we formed this particular additive manufacturing firm, ACE Micromatic Group. So in this particular AMACE solution, we are offering end-to-end solutions, starting from the powder characterization, make in India machines, printing of the parts, post processing, heat treatment, and validation and certification of the parts. So, this is the state of art facility in Bangalore, Pune. So, we will start with our presentation. I will give quick introduction of this particular global AM market overview. Already, everybody is knowing about this 3D printing, rapid prototyping, and then it is all so many names are there, so many things are there, and then it is more related to mechanical, computer, metallurgy, chemical. But if we see all these things, all are covered in the additive manufacturing, starting from the software development, machine development, characterization. So many things are there. If you see the in India, 2003 first machine has came installed in the CMTA, and then from 2003 to 2000 till the 2025, close to 250 machines are installed. But if you see the global market overview, it is going to $1 billion companies. Just I wanted to showcase that the 3D printing is booming continuously year by year, 19% per year by year. And there is some challenges are there also. But if you see $29 billion currently, it will go to next 3 4 years. It is goes to $100 billion company. So there is scopes are available in the additive manufacturing, starting from the I have taken. In the few slides, I will explain about the what are the steps and where the scopes are required, where the talents are required, or then particular education or research are required for this particular additive manufacturing. So this is the current scenario in India. If you are seeing this, currently Indian market is close to 900 crore. But if you compare with the global market, it is very less than 0.1% or 1% of the global market. So there's a huge demand, and then everybody you go with the starting from the EV manufacturing, aerospace, space, everybody is changing for additive manufacturing. And then there is a huge scope for this particular additive manufacturing. And then if you see 18% as compared to global 9%, we are growing in India 18% year by year. Currently, more than 120 non-metal 3D printing services are available. I'm talking about the plastic services below. If you go for this metal manufacturing, currently two are available, and more than 250 machines has been installed all over the India. Why I put this particular slides? If you wanted to see the where we are heading, the India is heading. There's a semiconductor industry is booming. There is a battery industry is booming, and then if you see IoT and all these things, the next industry is metal 3D printing or 3D printing industry, where everybody wanted to print immediate product to take the advantage of additive manufacturing. And there's a some government initiatives also started all these things. If you see this, Minister of Electronics and Information METI had drafted the policy for promoting 3D printing for the industrial grade also, and then for education also. Even also, government of India has established National Center for Additive Manufacturing and CAM, each region they wanted to put particular machines, and then they wanted to develop the skill development kind of things are there. And then multiple AM technology centers has been established. If you see just now, IIT has the three machine, IIT Madras. Same thing, IIT, so many IIT, NIT, they have started. Even some engineering colleges also with the DST funding kind of things are there. We have started all these things. And then the army, Indian army, actively integrated with additive manufacturing. Now you can see why Indian army came into picture. If you see all this particular, our Sukhoi, Russian jet engines are there, or Russian T-90 tanks are there. It has been purchased almost 30 years back, and half of this particular instrument, because of breakdown, they have not useful for this Indian army. So what exactly they are doing? They are doing the reverse engineering of CAD model, reverse engineering of actual product, reverse engineering of material itself. What are the current materials available in India, or what is the Russian grade? We are finding the alternate solution for this particular things. That is called as reverse engineering of that particular part. And then definitely all everybody knows ISRO is collaborated with the startups for the 3D printing for satellite components. If you take any startup companies in just like space companies, Bellatrix, Galactics, and then Skyroot, all are almost 80 to 90% parts they are going for this particular 3D printed parts. And then government also backed some incubator nurture startups developing 3D printed parts for the launch vehicles. So if you see, there is a key government initiatives are there. And then I will start with the some basic what are the current scenario of this particular 3D printings. If you see all these things, everybody knows all this additive manufacturing technology. Everybody knows powder bed technology, electron beam powder based fusion, powder energy densities, DED technology is there. If you see out of these, there are number of 20 number of technologies they have developed. We hardly know now particular 7 to 8 technologies, but now industry are moving towards the powder bed also, wire bed also, sheet bed also, rods, dispersion, filament, and pellet extruders. And more than 197 global machine tool manufacturers are there for this particular metal additive manufacturing. So this is the scenario of the metal additive manufacturing technology landscape. If you go for polymer, more than 17 different technologies are available for the polymer additive manufacturing. I will share this particular presentation to you also. And then more than 234 machine manufacturers are available for the polymer. Then same scenario is there for the ceramic additive manufacturing. Ceramic additive manufacturing, more than 12 technologies are available now. Just I wanted to showcase all this particular recent scenario in additive manufacturing. What are the recent scenarios are there? And this is the current process chain of this additive manufacturing. If you start with these particular things, initial engineering and software, you look after this particular opportunity where I can fit particular engineering and software. Can I do some CAD modeling course or this particular 3D printing? There is a simulation requirements are there. There is a so many softwares are available for the APS simulations, just like a Simifact, ANSYS, Entopology. So many softwares are available. What are the current designs are available? Can we put them some lattice structures which can be best suitable for additive manufacturing? And there is a design for additive manufacturing sir also. I have purposefully kept 2 slides for design for additive manufacturing. Like this is the last slide. There I will interact with all of you, the student. What is your understanding for additive manufacturing? If you start with engineering and software, then it will come to material. Definitely powder, wires are required. What are the material and powders are required? Some powder manufacturings are required. What are the powder characterizations is required? Some metallurgical analysis are required here. Chemical analysis are required. Where current material is not matching to the application, how I can modify the or chemically tweaking this particular material, and it can be best suitable for end applications. And definitely this is the core subject, laser process parameter. More than I am talking about the powder bed technology, where the this is the most popular technology in overall the world and India itself, where you have to play with the laser energy density, power, layer thickness, scanning speed, beam diameter. Apart from this is the laser parameter. More than 230 process parameters are available. How we can play with this process parameter, and then playing with this particular process parameter, how I can melt that particular alloy. To be frank, all weldable material available in this universe can be 3D printed. Currently, basket is almost close to 70 to 80 materials. Just now, I saw someone has written this particular high entropy alloys can be possible. If we play with the laser energy density, all these things, it's basic physics is there. We have to weld that particular powder, we have to melt it, and then produce a part. So we have to do all these things. Second thing is the printing. How we can print. I will not take all these particular things. It is required once you hands-on experience with this particular printers. What are the printers? How one single component or two different components we can place inside this particular bid platform. And definitely there is a post processing is required. We can't avoid this particular post processing. What are the conventional manufacturing processes are there? I don't think so. You have gone through the any additive manufacturing course in the engineering itself, because in engineering what we have learned is casting, forging, and fabrication, machining. What are the conventional manufacturing process are there? Same thing is there for the additive manufacturing. If I getting the mechanical property better in forging rather than casting, same thing we can achieve in additive manufacturing by applying heat treatment to improve the mechanical properties. Going forward is there the this is the qualification process are there. I have prepared yesterday only for this particular aerospace customer. What are the qualification process are there? Definitely all the qualification process are available for this additive manufacturing process, starting from the design validations. If you see this particular, I hope you can see my the screen. Yeah, this is the seat belt assembly. Vinod sir, can you hear me?
Yes, sir. Yes, sir.
Yeah, yeah, yeah. Good, good, good. So, if you see these particular things, this is the conventional seat belt assembly for the four wheeler, and then you can see the it has been reduced from 8 component into 1 component with the 40% lighter and 20% stronger. It can be manufactured by additive manufacturing process only. So how you are capable to design any CAD modeling, because manufacturing process is available, so we have to take the advantage of design for additive manufacturing. How you can combine? If you see, these 8 components has been coming to my factory. Okay, I am working in Maruti Suzuki or particular any Toyota company. And then we are purchasing 8 different components from 8 different suppliers. Because of any reason, one supplier has shut down his shop. The whole assembly has been stopped. So there is a called as supply chain reduction. Part count reduction is there also, but supplier, the independent of the supply part count of things are there. So where you have to see all this particular design for additive manufacturing. Second will be the material qualification. I already told you so many ASTM standards are available now for the powder testing. what are the powder testings are there, how I can play with the 20 micron to 60 micron powder for steel. Then same shift with the aluminum. I can go with the 40 micron parameter, 40 micron powder particle to 100 micron powder particle size. With this particular changing the particle size distribution from D10 to D15 to D19. And there is a huge scope are available for the metallurgy engineers also, where they can tweak this particular chemical composition for the end applications. There is just some challenges are there. In the few slides I will explain the challenges also for additive manufacturing. If we increase the carbon percentage from the powder particles, there is a crack propagation, crack initiations will come into pictures during the printing. So to avoid all these things, we have to tweak this particular chemical composition for additive manufacturing. And there's a huge scopes are available for the material characterization. Third is the process qualification. Definitely machine has to be calibration. So I will not touch this particular chicken because of we are hardcore machine builders. Uh, we can we have to follow this particular ASTM standards to qualify this particular machine for additive manufacturing with the micron level. What we have do we have to print in the micron level, we have to qualify. Fourth will be definitely will be the part qualifications. What part I have printed in the X, Y, and Z directions. I have noticed some question of anisotropy behavior in the previous lecture. Somebody has asked anisotropy behavior with the X, Y, and Z direction. Definitely, these anisotropies are there, but how we can avoid these particular things during these heat treatment conditions? There's so many heat treatment are available, and then we have to qualify this particular part, printing this tensile coupon in vertical direction or horizontal direction and 45 directions. As fabricated condition, what are the results are available? If we put this hash isotropic pressing, HIP, what will be the property? And then definitely some end heat treatment, maybe hardening, carburizing, nitriding, so many things are there according to the end application. Where the I want in forging high impact strength, I will go for different treatment cycles. If the rotational component for engine is required, where the cycle fatigues are required, so I will apply different treatment cycles. There's a part qualification process are there. And then we have to apply, so just now I explained post processing validations, and then document and traceability for aerospace. This is dedicatedly for aerospace required. I have to maintain one coupon. If you see, this is the build. I had to put one coupon with the date, and then for this aerospace, I had to maintain that particular coupon for next 20 years during the life cycle of that particular aerospace. This is the traceability kind of things are there. And then some certifications are available now. ASTM standards are available. And then if you see, Semilac is working continuously to validate this particular aerospace and airworthiness parts also. So yesterday I have prepared this slide. I will not go in detail because it is a too much complicated slide. But I wanted to highlight this here. More than 98 number of ASTM standards are available for additive manufacturing. If you start with the test method, what are the test method are available from the material specification, starting from the aluminum, ALSR 10 mg, titanium, and then cobalt chrome alloys. You can take any name, the standards are available for the test method, starting from the feedstock material, then process control, machine operation, testing and mechanical properties, and system performance. All the ASTM standards are available. I will share these particular things. You can download and then go for this particular what they are qualifying. IQ, OK, and PQ. Initial qualification, operational qualification, and performance qualification. How we can do this particular additive manufacturing qualifications are there. And then there is just so many another specific for medical, automobile, constructions, aerospace. This particular slide yesterday only I have prepared for some aerospace company only. So what I am to highlight to you, go to all these particular ASTM standards, look after what are the exact requirements are there, how industry is following this particular standards and making the parts. Somebody will ask of this particular repeatability and reliability of 3D printing components. So this standard will give the answer for this particular repeatability and reliability of these things. So going forward, there are key challenges are also available. Means we are facing, industry is facing. Just now I highlighted this. All the materials for this particular powder bed is available for the gas atomizer, then plasma atomizer. But if you see 2006 I started all this particular additive manufacturing close to 19 years back. The powders are coming 15,000 rupees per kg to 20,000 rupees per kg for SS316L. Simple stainless steel 316 grade powder. All are we are importing from the outside of India. But if you see current scenario, more than 6 to 7 Indian powder manufacturers are coming into pictures. But still, there is a limited powders are available because of the high equipment cost. Second thing is that powder cost definitely it is has been reduced to close to 1,100 from 11,000 to 1,000 rupees. Now industry is moving towards the water atomized powder. How chips from the machining can be milled and can be used for additive manufacturing. There is a material key challenges are there, and definitely there is a tweaking of chemical composition, limited knowledge of the applications, and then limited basket also for additive manufacturing. So some challenges are there. And then comparing to second point, comparing to China, currently all European and if you see compared to China and all these things, currently if you see the only 400 by 400 or close to 1 meter sizes are available with the particular limitation of one single laser or four lasers. But if you see China, they are coming with the more than 2 meter by 2 meter, where we can put big parts with 64 lasers. So definitely there is some challenges are there. As a Indian manufacturing, we are also putting our efforts. We started with 400, now we have moved to 650. Now we are going for 1 meter with increasing the lasers also. But we are coming drastically for the to achieve this productivity and size. And then if we compare with all these things, what is highlighting? Skilled workforces. Definitely, there's a skilled workforces are required because what engineering you have learned, mechanical, production, aerospace, metallurgy, material science, you have learned some basic manufacturing processes. Now the government, all the government, state government also taken the initiatives where they are included this coursework from the kindergarten itself. Now, if you see, I am putting what is this 2D sketch. What I am putting is 2D sketch, but there's a 3D paints are available where the kids are putting some wire forms and they are making their own toys. So the skilled workforce definitely it is going on all these particular things, but currently we are facing some challenges to see for the good application engineer. From AMACE perspective, what we are facing the challenges, good application perspective, good metallurgy perspective, good who is the handling for the my ANSYS or simulation software person, and then some definitely some marketing also required. But what you understand here, there's a complexity are freely available in additive manufacturing. The person who will put his out of box thinking, note down my point, out of box thinking, who will be the thinking out of box, he can develop the good design for additive manufacturing, putting his topology optimization, lattice structure knowledge. In the last slide I have kept two slides. Definitely we will give more time to that particular last slides. And definitely there is some challenges for the limited localizations. All, if you see, it has been developed by these Germans only. Now it has been shifted to China, India, all these things. What are the machine manufacturers, software manufacturer, powder manufacturer, spare part manufacturer, all are limited. And definitely some challenges are there. As printing conditions, we can achieve 5 to 6 array. Note down 5 to 6 array for the powder bed technology. If we require some assembly component, definitely some machinings are required. Currently, because of laser spot diameter is limited to 80 micron and powder particles are limited to 20 to 100 microns. Overall, 400 by 400 with a dimensional qualification, we can achieve plus minus 100 micron as printing conditions. If you more we wanted to achieve dimensional tolerances, we have to do for machining and some things are there. So again, the high equipment cost are there, but because of Indian manufacturers are came into pictures, more than 70% cost has been reduced of equipment cost. Just like the powder cost has been reduced, same thing equipment cost has reduced. If you see calculation, the what the component we are producing from the high equipment cost, definitely it will be higher. And then everybody is talking about the aerospace and space industry only because of high equipment cost, high powder cost. But definitely because of reducing the equipment cost and powder cost, it can be applicable for automobile. I will show you some automobile case studies also for you. So this is the current status or development happening in India with the powder bed manufacturing. So I will start with the some case study from this slide. So this is the slide where we have placed our machine with ISRO VSSC. These are 400 by 400 by 400 machines. In this particular 400 by 400 machines, we have modified, we have patented where anytime we can reduce 400 by 400 by machine to dia 120 by 200. Same machine, I can put this platform, and then the bid volume can be reduced to 120. So they have printed this particular noise reduction wall in ISRO. If you see, there's a transparency behind, there's a tensile coupons are there. So thin wall with the inconel material. Even also we don't know what material they have printed. This is printed in our machines, but there's just key challenges are there. So if you see, it cannot be possible by any conventional method. It can be only possible by additive manufacturing. How effectively we can design this part, it will be the best possible by additive manufacturing only. So I wanted to highlight this particular things. Second is, everybody knows the Gaganyaan mission, where the four person crew members now going for Gaganyaan missions. And then if they wanted to seat this particular Gaganyaan mission, it is a crew seat brackets we have printed, 3D printed. They have come previously, that is a conventional manufacturing. Nobody knows how they can manufacture all these particular things by conventional manufacturing. There's so many challenges are there, and the lead time is required for these particular things. They have 1 year for the conventional sheet metal manufacturing. They come, we splitted this particular crew seat. into 8 to 9 parts. We have printed successfully big parts. We have assembled, and then if you see, this is the cruise sheet brackets. More than 7 to 8 cruise sheet brackets. Now we are supplied to HSFC, ISRO for the Gaganyaan mission. This is our AMACE STLR machine where we have printed this particular cruise sheet brackets. Now, if you see all these things, this is Gaganyaan. Previously, not a single human and went to by spacecraft. So now they wanted to see from the outside the window. There is a no windows are available. Now they have modified. They have put some glass windows. So these brackets with the titanium we have printed, and it has been extensively tested with all the conditions, with the environment conditions, with the mechanical property, and then all these things are there. If you see one single assembly, how many parts are there? All we have printed in one single platform by nesting some parts here and here in single shot. Again, this is the EV, electrical vehicle. They wanted to launch the EV electrical vehicle. More than 70% parts. This is the platform 400 by 400. You can see we have printed this part vertically up by orientations. These are the supports. If you see, these are the supports to hold the part, and it acts like a heat dissipation also during the printing. This bike, more than 70% parts we have printed by 3D printing. Why? Because they wanted to launch the vehicle very early. And then three bikes we have printed. Then after that, they will went to commercial, conventional manufacturing process. But it has been went for Bharatmala trip. Starting from the Bangalore, it went to extreme cold condition to extreme hot conditions, and they have put some Guinness record or start going for 14,000. Why am I highlighting all these things? The 3D printed parts now continuously used with all these particular things. Actual use conditions rather than aerospace and space. This is the another case study. Yesterday I have presented it with the LRD semiconductor. Everybody is know about the semiconductor. What are the semiconductors? Everybody is chasing for semiconductor. This is called as cold plate. Conventionally it is a brazing, one single component, single second one, and this is third one, and they have been brazed with with what you see is conformer cooling channels. It is started from here, it will go like this, like this, like this, like this. Cannot be manufactured by conventional manufacturing process. If I wanted to go with conventional, I have to 1, 2, 3 single assemblies are required. We have merged these 3 single assembly with to one single assembly. Even we have modified some design. We have removed some weight in one single plate. 400, 1, 2, 3, 4, 5. 5 plates we have printed, and we are continuously giving some this additive manufacturing cold plates to industry. Definitely jet engines are there. Some jet engine parts we have printed. If you see inside this, can you see all these things? It is has been cut down these particular things. How complex shapes are there? The fuels are there. 300 micron holes are there for the fuels. 300 micron size. It cannot be possible by conventional manufacturing. Same thing. This is the discarded. Again, I am telling up discarded aerospace engine. But what exactly they are using for this? They have when the American company is there, they are purchasing all this discarded engine and they are using for power generation applications. But what are the blades? They have eroded. What they are doing? All these blades they are 3D printed and they are placing here and they are using for the power generation, energy application. Same aerospace engine they are using for the power generation applications. This is my own case studies are there where the 3D jet 3D printed jet engine we have printed in my previous organization with the 40 kg thread jet engine, where all these particular components we have printed. We have filed the patent also. It has been granted. So what are the jet engine also there for the drone application? So many applications are there. Small. We have printed and we have successfully tested also. Another case studies is there. If you see all the lattice structure designs, what are the lattice structure designs are available? The URSC satellite center, they have came for this particular brackets. And then if you see 524 height, our bed size is 400 by 400 by 400 only. So we have diagonally placed these particular things. We have given dummy walls. If you see, this is dummy walls for 200 micron dummy walls. It can be possible by additive manufacturing to hold that particular structures. It is a very delicate structures are available. So we have printed, we have removed the supports, and then we have successfully printed these components where the no dimensional limits are available. This is another case study. Why I am putting the case studies means different case studies, different applications are there. The if you see the conventional manufacturing, 100 sheet metal components, small sheet metal components they are taking and they are welding together. It required almost conventional manufacturing 2 months to manufacture these particular parts. We have printed with less than 24 hours, with reducing 100 parts into one single assembly, and we have successfully printed for the RF waveguide. It is a defense application where radar signals, they are sensing the radar signals. This is again this particular part validations for this particular space applications, where it is going for the NL and URSC application. Same thing, collimator we have printed. If you see along the 110 length, it is a 300 micron wall. All these walls are there. It is a 300 micron. Can be possible by additive manufacturing. Now the question will come into picture. It is a conventional design or we have modified. The good thing is there, as per the 3D printing requirement, we have modified these particular walls for 3D printing applications. And then if you see something is there to hold this particular part during the printing, we have given some supports, antenna supports, all these things by 3D printing. And recently, everybody knows this particular Chandrayaan mission. Chandrayaan 2 also and Chandrayaan 3 also. If you see what is this? National emblem of India. It is the 11th hour they had took the decision, URSC, to print these particular things. I will run this particular video. If you see, this is a rover. Once it has been landed to the moon, in the wheels, they have given this national emblem and Indian logo. What are the national emblem logos are there? We have 3D printed and it is went to now moon missions. So we are proudly say that 3D printed parts by AMACE, it is in now moon now. So there is no limits for this thinking design for additive manufacturing. Now question will come into this particular things are there. All I can showcase all these particular things is space, aerospace, automobiles, but there's a diamond industries are there. This is a battery casing for four-wheeler manufacturing. You can see this is the end component of battery casing. And this, if you see, this is the H13 base plate. Is a die This is a metal injection molding die where in this die the plastic injection molding will come, and this is the final product here there. So for this S13, there's a conventional straight holes are there. We have printed on this maraging steel, that is called as hybrid manufacturing, where the S13 has the high thermal conductivity and maraging steels has the high impact strength and high toughness are there. So combination of these particular things we have printed. Now question will come, why S13 and maraging steels? So there is a plastic injection molding dies are there. It's a high wear and tears are there. And if you see the plastic is taking top of this piece. So how to control all these particular things? We have to modify the design. This is the straight holes. If you see, these are so curvilinear holes are there along all these things. So what are the plastic will come? It will rapidly solidified because of that die, and then it will give clear cut advantage for additive manufacturing. After this printing, if you have done the 5-axis machining, you can see there is no gaps. Cycle time is 45 hours to print all these particular things. Now I can see the acceptable of this additive manufacturing or use of additive manufacturing. Everybody knows this particular tires, four-wheeler tires. What are the four-wheeler tires are there? There's a serrations are there. All the four-wheeler tires, there is a serrations are there. This is called as sipes. For the tire mode applications, we are printing millions of millions. Every month we are printing 10 lakh sipes for this particular tire industry. You take any tire industries of modes, we are printing this particular sipes. This has been modified manufacturing by additive manufacturing. If you go for conventional manufacturing process, the lead time is close to 1 5 months. Within 8 hours we are printed this size, we are putting the tire molds. Inside the tire molds we are putting these sides, and they will pour the rubber, and this serration will come. Now question will come, cost. Definitely cost. Comparing to conventional manufacturing, we have achieved the break even point, and then definitely it is the 20 to 25% cheaper than conventional manufacturing process. So all tire industries, all dental copings, what are the putting your dental caps, all knee joints and hip joints, now 90 to 100% has been printed by additive manufacturing process only. This is the now standard process to manufacture this part. It is a additive manufacturing process. So in between this has came. Okay. So these are the three machines are there. Currently, what AMACE is offering is dia STLR 120, STLR 180, and 400. But I have explained you, I can easily convert 400 inside the machine into dia 120 machines. So these are the three sizes are available by AMACE Solutions. It is a single phase STLR 120. More than 6 to 7 IITs or NITs we have installed, and this industry also STLR 400 is a industrial grade. We are now moving to bigger platform size machines also with 2 laser, 4 laser, 6 lasers also. So these are our installations. It is a DMRL and ISRO. Some installations we have done all these things, and then we have also installed in Manipal, ISC, IIT Bhilai, IIT Kharagpur, and MCB Military College also, and NCAM also, National Additive for Additive Manufacturing. So this is my last slide. So I have kept another 2 slides. All are listening these slides. Now what you can see here, what you can see, I can minimize this for the time being. Oh, it cannot be possible. Okay, so okay. If you see this, all these things, lady is lady is eating the Maggie, and then she wanted to cool the Maggie immediately. So what is called as? It is a jugaad, or we can call as a design also for simplicity of this particular things. Second thing is there the baby shower cap. You can see it has been designed. Nobody think about these particular things. How effectively we can design these particular things. It is called as out of box thinking. Third is, oh, babies wearing, what is this? Floor mat? Floor cleaning? Yes, no, this is wearing all these things, multiple use. Same thing, I drop. And then all these things. You can see it is a tie, umbrella, multiple use. The person is carrying the babies with the modification of current design. What to highlight is modification of current design or out of box design, where you wanted to do all this current design, how I can modify this current design with the additive manufacturing. So this is my last slide. Just I wanted to give some small things for industry requirements. I think I had to hard stop by 8:45. I have another call at 9 o'clock, so I will keep 10 minutes for the question and answer. So listen carefully. This is the last slide for these meetings. If you see, this is a 100 mm by 100 mm by 100 mm cube. You are all are engineers. What you can do for manufacturing? Either go for machining, either go for casting or fabrication kind of things are there. But if you see, this is the volume is 1 centimeter cube and surface is 6 centimeter cube. Can it can be go for additive manufacturing? No. So if I put some holes in this particular cube, if you see volume to surface ratio, it has been increased to 25.78. And then operations, I have to drill 54 holes by drilling operation, milling operation. Two operation has been increased. So lead time has been increased. Then if I put some hollow inside this also, this I have put some hollow one side. So volume has been decreased by 1 centimeter cube to zero point 0.8, but surface has been increased. The complexity has been increased. Then closed hollow. So what I wanted to highlight here, what are the topology optimization tools are available? You can note down N topologies available for education license. Autodesk, AutoFab, NetFab is available for education free of cost. You start putting what are the GrabCADs models are available, how I can put some complexity, how I can put topology optimization, how I can put the lattice structures and can be best suitable for additive manufacturing, because conventional manufacturing design, if I take my simple example day to day life, I will take mouse, I will take laptop. It has been manufacturing by additive manufacturing. How you can think about the out of box thinking, it will be you will be the best suitable for industry kind of things are there. Conventional manufacturing definitely the cost come into picture, and there's a established process are there. How we can utilize this particular design for additive manufacturing. Some case studies are there. I will not go to this particular thing. So I will stop this particular slide, and then where are we? Okay, I will stop this, and then I will come back here. So I will turn on my camera also. Hope I am visible. I can see all of you. Can you see me?
No, sir, your camera is not visible, sir.
Oh, is it? Something is there. Okay, let it be. Yeah.
Yes, sir. Now you are visible, sir.
Hmm. Okay. So I have purposefully now 2037. So we will go with this particular feedback section. I will open these particular things. So can we go with the questions?
Yes, sir. Actually, Manigandan asked one question, sir. Surface finish for 3D printing or minimum value till till for your product. So he's asking something about the surface finish of the product, what you've shown in that in your case study, sir. Minimum surface finish.
Good, good questions. See, I will tell you, if I print aluminum ALS at NMG, it is a less weight material. During the printing, it will agglomerate the surrounding particles. So as printing condition, we can achieve 7 to 8 RA. And then after polishing, there's a short blasting, glass bead blastings are available, where we can improve up to 1 to 2 RA. For SS316, as printing conditions with 30 micron layer thickness, we can achieve 3 to 4 RA. It all depends upon the layer thickness. 30 micron, I can go for 100 micron. What are the powder particle size are available? I can go for 80 micron powder particle size, or can I reduce down this particular powder particle size? And there is a called as hatching. In one laser path, how I can overmelt this hatch distance. It is all depends upon the overlap the hatch distances are there. So we can definitely improve. Currently, surface finish is close to 4 to 5 RA for additive manufacturing. Oh, what are the main limitations of current additive manufacturing techniques? How you seen evolving in next 5 to 10 years? So I will tell you main limitations. Now, space industry, if you see, we are the second largest starters of space industries. So there's a big components are required for the internal government also. So there's a one limitation currently as a machine manufacturer. What we are seeing the large size machines. Currently available machine sizes are 400 by 400, but definitely 1 meter or 2 meter with multiple lasers are required. This is the current challenges are there, and definitely powders are limited or available. So we this is the few challenges are there, limitations of this additive manufacturing. How do you approach material selections? Okay, there's a two way I can answer the material selection. First is the end applications. If my end application is aerospace or forging punches or something is there, there's an end application, there's a end mechanical properties are required. To map this end mechanical property, I will go to backward integrations where I can see my current basket is available. SS basket, inconel basket, titanium basket. How I can match this mechanical property. That is called as material selections. That way I can do the material selection. Second thing is there, how I can tweak the new material. Means conventional manufacturing for the gas turbine, or this is the CM247, but it's difficult for additive manufacturing. I can select this material, how I can tweak this material. Some chemical compositions are there. There's a upper limit and lower limits are there. I can tweak it. I can stabilize it. for the crack free, and I can start with the 3D printing kind of things are there. That way we can do the material selections, and definitely the sources are available. It is the import sources are there, or local made sources are there. Then that way we can select this particular material. Third question is what industry is future to start on AI and why? See, the fastest growth in additive manufacturing previously, as you can see, it is space and aerospace because of affordability, high equipment cost, high product cost. So aerospace space where I can reduce 1 gram of material in the whole aircraft. This is a close to 400-ton aircraft. If I reduce 1 gram of material over the 20 years of lifespan of this particular aerospace, I can huge saving of carbon footprint where the fuel savings are there. So that's why there's affordability is there. They can put some money on these particular things, aerospace. But scenario has been totally changed now. Now the biggest adoption is happening in medical. All mandibular, maxillofacial, craniofacial, stent, heart stent, hip implant, knee implants, all medical industry, 99% are they are going for additive manufacturing. So I can see the fastest growth adoption is in medical industry. Oh, how AI and machine learning. Recently, I had took two PhDs in from NRTK. To be frank, I will tell you this is all are mechanical backgrounds, and they have done in the additive manufacturing with Shrikant Bunda sir. Within 6 months, they have developed more than six softwares with AI. Now ChatGPT is available, DeepSeek is available, GitHub is there available. Whatever what I wanted to do, we can program it, and then AI for AI for process parameter optimization. If I take new material, how rather than playing design of experiment, printing and testing, can my AI tool suggest optimize the process parameter? That tool we had developed. Close control loop monitoring. During the printing something is happening, how I can see the process control monitoring, that we can do. So many things are there. AI we have to, machine learning, it will go side by side. Definitely we are doing something, we are filing the patent also. And then design for additive manufacturing, definitely this is the first step of 3D printing. We have to go for design for additive manufacturing. There are some algorithms are there. Just one algorithm I have shared with you, complexity, volume to surface ratio. Apart from this, there is just so many algorithms are there where AI can help you to minimize the design of experiment. And definitely we will take the advantage of AI itself. Fifth question is what are the most promising development in multi-metal or functionally graded metal? Okay, good. Something is cooking with the functionally graded material, and with the DED technology. DED means where the wire and powder we are putting in the top, with the nozzle it is melting and it is printing. That is functionally graded material. We are doing something for the again aerospace application where the end applications required. And then multi-material also we are putting some neobium in the in conal and adding something is there. I can't disclose this particular end application, but there are few hundreds of papers are available with the universities. You can do, you can check also. Sixth question is how does AM affect the life cycle performance? I think I have shared one this particular case study, EV bike also. Apart from this, if you see the, I will take one example of Mahindra Bolero example. Now they are launching the Mahindra Bolero EV kind of things are there, and they are checked the recyclability and repeatability also. the end customer I had disclosed, where we have printed more than 6 to 7 parts for this Mahindra and Mahindra, and then definitely there's a life cycles are there, life cycle performance are there. I will go to next question. 3D printing minimum diameter from a micro hole. So we have printed 300 micron size hole. Just now I have explained with this particular 3D thruster. I showed one case study also where we have printed 300 micron. There's some limitations are there because of spot size. What we are using, the laser spot diameter is 80 micron, and then powder particles 80 micron, 200 and 120 micron. Then the heat affected zone, spot diameter is 80 micron, heat affected zone is 150 micron, and then second layer is will come. So minimum 300 micron we have achieved. So if you reduce down this particular spot diameter to 30 to 40 micron, we can achieve up to 100 micron small micro holes. How to reduce 3D printing time consuming process? Oh, there's so many things are available for the reduce the 3D printing time. Previously, it is a one laser with scan speed of 1000 mm per second. Now we have increased the scan speed laser 7 meter per second with two laser, with four laser, with eight laser. Same part I wanted to print one single laser. It required 2 hours. If I print with the four laser, it required half an hour. And same thing we can do the process optimization. If I wanted to print this particular things vertically, it required 3 hours. Same thing I can put horizontally, it required 30 minutes to 40 minutes. How effectively we can orient the part, we can nest inside the build, and then multiple lasers we can introduce where we can save the time. Currently 20 cc per hour to 1000 cc per hour machines are available for additive manufacturing. And then the layer thickness, if I print with 30 micron layer thickness to 100 micron layer thickness, the time will increase where I had to give some more energy density. How close are we using AM for large scale production of EV parts rather than just prototype or low volume components? Yes, we are very close, definitely. See, I will tell you, we are going with one directions. We are giving the solution for EVs. EV is going for their directions. Means there is a limitations are there. Means if I take one particular company, they wanted to go for conventional diesel or petrol engine to EV. They have some limited time to launch that particular vehicle, limited space, and then all these things are there. For time constraint, they are coming to additive manufacturing, and then we are printing. This is the current scenario. What are the time constraints are there? They are coming. There we are 3D printing. Immediately they go for testing, validation, and they're launching product. And then for prototype to mass production, they are going for the conventional manufacturing. But very soon, because of low volume productions, limitations of sizes, time, and cost, there is a high equipment cost of the machine, powder cost. If I print with high equipment cost, with the 7 year capex cost, with the powder cost, definitely the 3D printing cost is currently part cost is costlier than 40% by conventional manufacturing. If I reduce down the equipment cost, multiple powder manufacturing will come into picture. We will match. Now currently tire types what I have shown you, we are going for additive manufacturing. EV product also, some gears we are printing for mass production now for electrical two-wheeler vehicles. But it requires some time. We are close now. Okay. As presentation contact number. I have given my first slide the number and email ID, and then sir will give you all this my email ID and mobile number also. Anytime you can call me, you can email me if you want. Some workshop conduct things are there. We are organizing continuously workshops for educating the colleges, engineering colleges, even also high school level also we are going for this particular, because education is most important in additive manufacturing. So we have started with the education vertical also, where we are giving this some workshop, 2 days workshop, 7 days workshop are there available. You can check with our website also. Continuously, we can you can follow with this particular LinkedIn also, where we are continuously posting some workshops, where you can see. And then I will put my email ID here, where you can, you if you have something in your mind, you can reach out to me. Anything another questions? I can see only two persons they are putting some questions.
No, sir. A lot of people posted the questions. I organized and given to you
Okay.
in the sequence.
Okay, okay, sir. Okay, sir. Okay, sir.
Some of the things are not updated here. That's why I
Sure,
cumulatively
sure,
posted
sir.
questions.
Sure, sir.
Participants, if you have any doubts, still you have means you may ask, unmute yourself and ask, or else you directly post your questions in.
I have given my personal number also. You can give the reference of TGS college and put me some questions also. I will definitely try to answer, or I will connect you to our application team members also. So I can see it from 2006 to 2025. After 2018 only the 3D printing has started growing. It is a learning curve only after 2018, and 2018 onwards it is started moving now. So every college, personally 2010 and 11, I personally going to each and every college to give this particular additive manufacturing lectures. So good to see you. Thanks to Ram Prabhu sir also. He only connected with these particular things.
Yes, sir. So, participants, do you have any questions? Okay, sir.
We would like to conduct workshops, so definitely we will plan. If your college or institute want to do workshop also, we will come for the 1 day workshop also. We'll give hands on. If you wanted to join industry also, we have some workshop kind of things are there. And then I will connect you with this the right person, where you can get the industry exposure also, where you can spend some half day with industry with the machine, and then half day in the classroom training is also available. Both way we can start also. In Hyderabad itself, we have installed three machines also now. One is in NCAM, one is in DMRL. Now third machine is coming to MCME college, is military college. Let's see where, with collaboration with NCAM, we can start all this particular Hyderabad itself, some workshop.
Dear participants, do you have any queries?
Okay, then
Okay, sir.
I have 5 minutes left. 9 o'clock. I have another meeting. Sorry.
Sure, sir. Sure,
Uh,
sir. We will end it, sir. If you have any questions I received, I will post it to you. So we
sure,
will give that things to them, sir. So
sure, sure.
on So we are come to the end of the session. On behalf of the organizer and all participants, I will take this opportunity to sincerely thank our esteemed resource person, Mr. Shreyans for delivering such an insightful and engaging session today. Surely your expertise and valuable inputs and practical perspective have enriched our understanding and made this session is truly meaningful, sir. Surely we are
Sure.
grateful for your time and effort and dedication to engage in this session, sir. So once again, I'm thanking you on behalf of our college
Thank you.
and all
Thank
the
you.
participants, sir. Thank you, sir.
Thank you. Thank you. Best of luck, all of you. Thank you.
Thank you,
Bye
sir.
bye.
The participant, I will share the feedback link for both sessions. Uh, you will fill the feedback. Except in the chat box, we won't post feedback anywhere. Don't personally ping to me because it is mandatory to attend the sessions because everything is recorded. How many times you are being in the session and everything. So I pinned the message of the postcard link. So it consists of both the sessions. For session 3 and session 4, you want to fill the feedback for both sessions. So tomorrow also we have a session. So one for uh, med- medical printing, 3D printings, and another from lightweight manufacturing of uh, aluminum alloys for industries, industrial applications.